is really neat. I mean, imagine New York subway, right? And there's a little number up there. This is, or a big yellow light blinking. Oh, don't worry, there's gas at this level, right? It has to be monitored real time. Or what they're, I can see that in the future, but the odds of these sensors being electrochemical are really high. You just have to find something that reacts with that compound in particular. And they've done that for a number of compounds. So the easy ones are done, right? The easy ones are some gases like nitric oxide and oxygen. Those were some of the first ones. But now they're getting into brain chemistry. They're getting into neurotransmitters. And now they're getting even more specific, right? These sensors that can detect certain sequences in DNA. So in that sense, I've always felt electrochemistry as being really clean. In other words, it's very particular in that sense. And if you can get something that will sense just one single compound, it's awesome. So that's where we're really at today. We're not going to be talking about these particular sensors, but we could just as well. The calculations would be the same. So here's an example. We've got a cell. If it was one of those transmitters, it'd be the same idea. You'd have a cell. The cell notation, you'd still have a cell notation. The below cell describes a probe that can determine the concentration of chloride in an unsaturated solution. So I don't know if you recognize this, but this is that that standard hydrogen electrode. Here's a question. See if anyone remembers this. What was I doing? I was looking at some physics forum, and these physics guys, they couldn't remember this. And then I was looking at this thinking, anyway, here's the point. Why does this say 1 bar? And why is that significant? It's a tough question.
Do you need it in the K?
It has a lot to do with the K.
It's in the right units.
Because it's in the right units. Exactly. And when we have our expression, whenever you're relating Gibbs free energy, and we have an expression, I think it was minus NF E cell or something, right? But we have some expressions for E that can get us the equilibrium constant, and we got a quiz on it, right? The equilibrium constant, there were 2 types of equilibrium constants. This is more information than you need, but it answers the question. We had a K and a KC. We're doing thermodynamics. We're using the thermodynamic equilibrium constant. So that means gases need to be in bars. Well, why do gases need to be in bars? Here's an even underlying question. And Jeff should have the answer to this, because we just talked about it in PChem. Standard states. All these equilibrium constants, yeah, they're products over reactants, but all with respect to their standard states. It's activities. And activities with respect to their standard states. So don't you usually wonder why you can take the log of K's and raise them to the powers? They're supposed to be unitless. You can't have a power or a unit and a power. And they are unitless because everything's with respect to its standard state. So the point is that the standard state has the units of bars, not atmospheres, for the thermodynamic equilibrium constant. That's why it's a big deal. That's why it needs to be 1 bar. Anyway, okay, you didn't need to know all that, but the point is that just got me thinking. So what's the point of this? The point of this is, let's see if we can, the big point is this. Giving a measured cell potential, find the concentration of chloride. Okay, so they're going to measure some voltage, and just from measuring the voltage, you should be able to calculate the concentration of chloride. Well, to do that, we need to write reactions for each half cell, a balanced net cell reaction, and then write the Nernst equation. And in that Nernst equation is going to have the concentration of chloride. We're going to know every single variable in that Nernst equation except the concentration of chloride. We're just going to mathematically solve for it. That's all this whole sensor application is that Nernst equation, and you solve for the compound you're interested in the Nernst equation. Because you know everything else. Everything else is defined. Okay? So how do you get there? We got to start with part A. Write the reactions for each half cell. So I think it'll be easier to see the big picture once it's all done, but let's just start with the beginning here. Ida, what would be the half reactions for each half cell? Now the cell notation gave you the clue if you remember how to do it. Right? Like if you take a look at this, right, the anode, the standard hydrogen electrode. What goes to what? Because it looks complicated. But, and usually you can pick it out up here. But it's not up there. I didn't give you that table. What goes to what? You recognize it? Do you recognize what I underlined as being one cell, or one half reaction, the other one being the other half reaction? Where does the arrow go? The arrow is pretty much where the what is? The line. The line. That's really where the arrow goes, right? And then sometimes it might not be a line. It might be a comma if these two are in the same state. But here's the line. So our arrow is going to be right there. And then what is this PT solid doing there? You have to know a little bit about the standard hydrogen electrode to answer this. It's a, there's the C, catalyst. It's a catalyst. Otherwise, you're not going to get this reaction to proceed. Hydrogen gas won't get converted to hydrogen ion. So the catalyst, it just makes the reaction happen a lot what? Faster, easier. It lowers, ooh, Kimberly, it lowers its activation energy. Very good. Okay. So if I'm going to replace that with an arrow, right, I'll have H2 gas on this side, H plus over here. Now we just have to remember how to do this, Jackie. How are you going to finish this half reaction? How do you make it balanced? Yeah, but I would balance the H's first, though. Yeah, put a 2 in front of it. Now do the electrons. Two of them on the reactant or product side. Perfect. Okay. Now, if you remember, let's put our E zeros over here. What is the potential, Brandy, for the standard hydrogen electrode? It's supposed to be. I don't know if you remember, but it's the potential that all of the others are measured with respect to. This one is set exactly at 0. 0.00 volts. It's set exactly at 0. And if you're not comfortable with this, you can just dig through all the tables and find it. But the point is, here it wasn't given. So on an exam or a quiz, it may not be given. So it's something that you should know. And if you wanted to be particular, I guess you could write the little platinum catalyst on the arrow, because special conditions are usually written on the arrow, but we'll just leave it out. It looks more confusing. How about the other half reaction, Danielle? How would you write that one? What goes to what? Good. AgCl solid goes to yeah, because the arrow's just pretty much there. Chloride and Ag solid. Something is messed up there, isn't it? We better. Oh, is that a possible half reaction? It is. Wow, I thought it made a typo. So where do we put the E? Oh, I shouldn't have pointed that out because that's funky. Let's say you can't. Don't look at the table. Where do you put the electron? Right, because it has to have the same charge on both sides. I thought I made a typo, but I didn't. All right, that is a funky one. Okay. How about? Oh, I've got 2 to pick from for that. And I could also flip it. Remember? What number, what potential should I write for that half reaction, Marlena? 0.197? Does everybody agree? The 0.197 is for a what solution? Saturated KCl. So that would have to be written here and say that the solution is saturated in chloride. And if the solution was saturated in chloride, and if you want to find the concentration of chlorine, that's just going to be a KSP problem. So it's not saturated in chloride. It needs to have said it too anyway, and it didn't. So you should pick the 0.222. So these are the standard potentials. Okay. Oh, but hey, if we add them up though, we can't add them up like this though, Kimberly. Did we write down the right number? Because what do we have to do to this bottom reaction? You see it?
We did write down the right number. We just have to
Yeah, so if I multiply this by 2, remember, do I multiply the 0.222 by 2? No, don't multiply the 0.222 by 2. These are intensive properties. So they'll cancel. But we need to have the right overall reaction because you're going to write the Nernst equation from this. And if you don't have the right Nernst equation written, you're not going to have the right reaction quotient or equilibrium constant expression written. So this is a big deal. You got to make sure you get this right. Okay, so I'll have H2 gas. What else do I have on the reactant side? Silver chloride solid. And that goes to a couple hydrogen ions and a couple chlorides and a couple silver solids and 0.222 volts. Okay.
What did we do? HCl?
Did I forget? Oh, I forgot to multiply that by 2, didn't I? Thank you very much. I didn't miss anything else, did I? Okay, so we wrote the reactions for each half cell. We wrote a balanced net cell reaction. Now they want us to write the Nernst equation. Okay. Let's have Jeffrey. Jeffrey, how would you write the Nernst equation for this thing? What equals what? E cell equals 0.222 volts. Okay, log of Q. Now let's write an expression for that Q. I'm glad you didn't give us everything. I gave Gloriana something to do. It's going to be what over what for Q, that Q expression, according to our overall balanced reaction there.
AgCl over
Products over reactants. AgCl is a reactant.
Okay, so all of that over.
Well, is it be specific? What would I write?
H plus Cl plus AG.
In what? Be specific. H plus in?
In
How do you write equilibrium constant expressions? H plus is in? Someone help her out?
Concentration.
Brackets. Okay, now you know what I'm doing? Okay, now keep going. H plus in brackets.
squared.
Squared. Perfect. Keep going. Ah, what happened there? Look at that. Okay. Then what?
Cl in brackets squared.
Perfect.
Ag in brackets. Oh no, solid.
She got it. Okay, good. Keep going.
Okay, so over H2 in brackets.
Okay, here. No, it's not in brackets though. Do you remember? Has to be a. Someone said it. Has to be a big P. A little subscript. Now, is it squared or anything? Nope. Just a 1 in front. Okay. So in these expressions, right, gases have to be their pressure, okay, in bars. That's why it was given up there. Okay, so that is our Nernst equation. Okay. In fact, could have put in the numbers for H plus and the pressure of the hydrogen, but this is okay. Okay. So if you wrote in the numbers for hydrogen ion and the pressure, that works. You just don't have anything for the chloride to put in. Given a measured cell voltage of 0.485 volts. So now where are they getting this 0.485 volts from?
Is that the E cell? I don't know.
Yeah, that's the E cell, but where are you getting it from? You're actually doing this.
Is it from the table that you have there?
Oh, it's not from a table. Yeah, there's going to be some little computer, some little voltmeter that has these little, that's hooked up to this cell. And it's going to be reading 0.485 volts. But you're right, though. That was the E cell. Okay. So do you see how once you plug in E cell, the 0.485 volts, and then what do we plug in for? So that's going to be 0.485 volts, 0.222 volts, 0.05916 all over 2, log of, what are we going to put in for this stuff? Because we should have numbers, Sabina, for everything but that chloride, because we got to solve for the chloride. So what are you going to put in for hydrogen ion? Where is it? There it is. What are you going to put in for hydrogen ion? Right. And what do they want? What does the brackets H plus mean? It means concentration. So what is the concentration of hydrogen ion? Use the pH to find the concentration. Okay. So yeah, I would be careful. So I would do what Monica said and not skip anything. Use the pH to find the concentration of hydrogen ion.
Is it a negative pH?
If pH is 3.6, concentration of hydrogen ion is going to be what?
Negative pH times
10 to the negative 3.6. If you have,
3.6 or 3.6? Negative 3.6, right?
right, because let's see if you remember this.
So it's 2.5 times 10 to the negative 4.
Yeah, that sounds right. If you have P of anything is the negative log of that thing, right? So you can find, oh, I should write X or something, right? Let's write X or something. Px is the negative log of X. So you can find X by just raising both sides to the 10 power. So 10 to the, I should write it on the other side, it'll look better. 10 to the negative Px is my X. That works for anything. Works for any P function. So concentration of hydrogen ion is 10 to the negative 3.6. And what did you, Andy or someone told me the answer. What was it?
2.5 times 10 to the negative 4 squared.
Squared, perfect. Chloride, squared. And for the pH2, everybody, I should put in 1 bar, or 1. All these units disappear because of with respect to their standard states that we talked about before. So now you got to solve for chloride. And you're done. See if you can get it. I got 0.15. That's pretty close to what you got. So it depends on your rounding, I think, but
Yeah, definitely.
I didn't do any rounding. If you didn't get it, I brought the 0.222 over first, then I multiplied it by 2, divided it by 0.0596, made it negative, because I have a negative sign, raised it to the 10 power, divided it by 2.5 to the negative 4 squared, then whatever I got, I took the square root. Hopefully you can get it to work. So the rest is homework.
Huh? I got like 0.143. You got 0.155. And Jeff got 0.14.
Maybe, what did you use for the concentration of hydrogen? I just used the number that Andy gave.
I used 2.51 times.
Yeah, it might have more digits. So
Well, know what?
you'll get a
Actually,
different
I
answer.
think I used what was in my calculator. Well, actually, no,
Yeah.
no. I used 2.51 times the name.
Yeah, that might do it.
That'll definitely do it. Yeah. Especially with all the junk you have to do to get the answer.
So with the rest of the period, I suggest working together, and if you or the folks around you don't know how to start out or work a particular problem, just ask. The numerical answers are on the bottom. So see how much of this you can get done, because this is your homework.